probably seen one of these, right? These incredible 3D models made by drones. They look just stunning. So realistic, you feel like you could reach out and touch them. But what if I told you that this beautiful, perfect-looking model might actually be a lie? Let's dig in and find out what's really going on. So, this is the big question. The whole reason we're here. Can a map that looks absolutely flawless on screen be completely wrong in the real world? The short answer, oh yeah, absolutely. And knowing why is super important for anyone who actually needs to use this data for real work. All right, so to get to the bottom of this, we first have to unpack what I like to call the beautiful lie of a drone map. This is that huge gap between what looks good to the eye and what's actually accurate on the ground. Okay, so the basic idea is pretty simple. You have a drone flying a precise grid over an area, and it's just snapping away, taking hundreds, maybe even thousands of photos. And the key is that all these photos overlap. Then, some really smart software takes all that visual data and stitches it together to build that seamless 3D model we saw. But here's the catch. Here is the lie. If you don't give that model any real-world reference points, it's basically just floating in digital space. I mean, it looks right, but the whole thing could be shifted a few meters to the north, or tilted by a degree, or the scale could be just a little bit off. Now, for just looking at a pretty picture, who cares? But for an engineer trying to build something, that's a total disaster. So, how do we fix this? How do we take that beautiful floating model and lock it down to its exact spot on planet Earth? Well, that's exactly what we're going to cover right now. The answer is something called a ground control point, or a GCP. And you should think of it literally, like an anchor for a ship. It's a physical target you can see on the ground, and its exact GPS coordinates have been measured with super precise survey gear. You basically tell the software, see this little pixel in my photos? In the real world, it is exactly at this latitude, longitude, and elevation. That's what anchors the whole map down. But you know, anchoring the map is only half the job. You also have to prove that it's accurate. And that's where a second kind of point comes in, the checkpoint, or CP. So think of it like this. If the GCPs are the anchors you use to build and calibrate the map, the checkpoints are like the independent auditors who come in afterward to make sure you did your job right.
Okay, so we've got our map anchored, and we've got our auditors ready to check the work. But how do we boil all that down to a single, simple number that tells us how accurate our map really is?
We do that with something called the root mean square error, or RMS error. Now, I know it sounds a little technical, but the idea is actually really simple. It's just the average difference between where your drone map thinks a point is and where that point actually is on the ground. The smaller the RMS number, the better your map. Simple as that. So what's a good number look like in the real world? Well, if you're doing serious work like calculating dirt volumes for a construction project, seeing an RMS error around plus or minus 3 centimeters, that's fantastic. That's the kind of number that lets an engineer sleep at night, knowing they can trust the data. And this is so important to understand. The RMS error on your ground control points tells you how well the model fit your anchors. But it's the RMS error on your checkpoints, those independent auditors. That is the ultimate test. That number is the real, honest proof of your map's accuracy in the real world. Okay, so we've got anchors, auditors, and a final score. But how in the world does the software turn a bunch of flat 2D photos into a complex 3D model to begin with? It kind of feels like magic, right? Well, let's pop the hood and take a quick look at how it works. So, it all kicks off with the drone grabbing all those overlapping pictures. Then, the software dives in and starts finding unique features in every single photo, like the corner of a rock or a specific leaf. Next, and this is the really clever part, it matches those exact same points across dozens of different photos. Finally, using a bit of geometry called triangulation, it calculates the exact 3D position of each point, building this massive point cloud that becomes the skeleton of our model. And really, the whole process boils down to this one simple idea. It's the same reason you have two eyes. It gives you depth perception. If you see the same object from two slightly different angles, your brain can figure out how far away it is. The software does the exact same thing, but it does it for millions of points from hundreds of angles to build that incredibly detailed 3D space. Okay, so that was the tech. Pretty cool, right? But now let's bring it all back home, back to the real world, where accuracy isn't just a nice-to-have, it's a non-negotiable requirement. Look, for engineers, for construction managers, for surveyors, accuracy is everything. It's the foundation of their entire job. If they make a critical decision based on a map that's off by even a few centimeters, it can lead to huge costs, major delays, and even serious safety problems. The beautiful lie just isn't an option. And this isn't just some vague idea. These are real official standards. Just look at this table here, which is based on guidelines from the Public Works Department, or JKR. You can see right away that different jobs demand different levels of accuracy. For general road design, maybe you can get away with 10 centimeters of error. But if you're building a bridge or defining a legal property line, you have to be accurate down to 1 or 2 centimeters. There's no room for error.
So, if you only take away a few things from this explainer, let it be these 4 points. 1. GCPs anchor the map. 2. Checkpoints, or CPs, prove the map. 3. The RMS error is what scores the map's accuracy. And 4, and this is the big one, professional work demands professional standards. A pretty picture is not enough.
And that brings us to the final question I want to leave you with. Now that you know about the beautiful lie, the next time somebody shows you a drone map for a serious project, are you just going to say, wow, that looks great? Or are you going to have the knowledge and the confidence to ask the most important question of all, can I see the quality report?